Hey physics students, today we are going to be talking about the conservation of energy in several different situations. We'll be utilizing our energy and work equations from our AP Physics equation sheet. Let's get started. What is the conservation of energy? The conservation of energy is simply the energy before is equal to the energy after. We see this throughout all of science, and specifically in physics, we're talking about kinetic energy, spring potential energy, and gravitational potential energy. We may also have some thermal energy that may be lost. Typically, we don't really look at that in physics problems. We just pretend they're perfect situations. Now, if I write this all the way out, we'll say the kinetic energy before plus the spring energy before plus my gravitational potential energy before is equal to my final kinetic plus my spring final plus my gravitational potential final. Now it's a lot to write out, but what's important is that I have the transfer of energy, and this is what we're going to explore. We're going to look at a variety of situations and apply this equation to those situations and see how does my energy transfer. My first and most simple situation is something that is falling. And in this particular example, we have someone who's falling from point Y all the way down to a height of 0. Now, I like to get these problems started by writing down my energy equation on both sides. I'm going to write them all out, and eventually we kind of get to the point where we're able to eliminate them to start, but right now we're kind of focusing on what we fully understand. So initially, I have this entire equation, and we're not going to be using all of that, and this is the most important part, I think, about the energy equation. So at first, this guy is just standing on top at this height of Y. Now we know on both sides I have no spring energy. Now before he starts, we know he's not moving, so we can get rid of that kinetic energy. Now when he hits the bottom here, we know I no longer have potential energy, I have no height. That simplifies our equation to the potential energy before equals the kinetic energy after. And I can use this equation pretty simply. Mass times gravity times height equals 1/2 mv squared. Now from here I can plug in different things, but something I find important is that actually my masses cancel. So we're talking about potential and kinetic energy, specifically in this situation without a spring, my mass doesn't matter. Here's a really cool connection to this equation. Now if I go to my equation sheet and I look at my kinematics equation, I have this equation right here. And I'm going to show you how these two are actually the same. So if I look at this situation, I know I do not have an initial velocity, which gives me Vf squared equals 2a delta x. Now let's go back to the derived equation from above, and let's solve for v squared. That'll give me 2gh equals v squared. That's the same exact thing as my kinematic equation. The only difference is that I wrote different pieces for my variables. This is a really big connection right now between our energy and our motion. Now before we move on to some different situations, let's talk a little bit about the loss of energy. Now remember our equation here. This is saying that all the energy before is equal to all the energy after. Now we know in a real life situation, for instance, if I drop a ball, goes down and hits the ground, and then it bounces back up to this height, throughout this whole situation, the total energy is going to stay the same. But right down here, my energy is actually transferred into my thermal or sound energy. So sometimes we like to call this lost energy. And this is something that you are going to be exploring through a lab. So you'll be figuring out my potential energy, my kinetic energy, and then my new potential energy, therefore what is lost. Now before we move on, let's think about this. My potential energy when this is at the top would be mgh. And this is actually equal to my total energy the whole time in my system, because as this goes down, my potential energy is transferred into kinetic energy. So at the very bottom, that means my kinetic energy is equal to my total. Let's move on to some spring problems. Let's talk a little bit about springs. Springs are something that we're going to introduce and then come back to later when we talk about simple harmonic motion. Now let's say I have this situation and I have a mass that is put on a spring and then it goes all the way down. Now this is actually a really cool lab because you are able to figure out how much mass do I need to get something to just touch the ground. Now when I think about this, at the very start right here, I have my maximum for my potential energy. That's my gravitational potential energy. Why? I have no stretch. Then this thing is going to fall down, and at the very bottom, all my energy has turned into spring potential energy. Now you may be saying, where's kinetic? Well, it starts at no velocity and it ends at no velocity before it goes back up. So this one's pretty easy to go through. So I start with gravitational potential energy is equal to my spring potential energy. We know my equations are mgh and then 1/2 kx squared. Now you'll notice the mass doesn't cancel, which makes sense because my spring potential energy does not have mass in it. Now where could we go from here? There's a lot of different pieces. For example, a common lab is to solve for this mass. So I have 1/2 kx squared over gh. Now when you initially look at this, you may say, aren't x and h the same thing? They're not. Remember, x is actually the stretch of the spring, and my height is my distance from the start to the end. These are not necessarily the same, but they are often very close. Another situation we have is a horizontal spring. Now if I think about this that's moving back and forth, oscillating, often we look at when it's at its equilibrium point and then when it's at its maximum point. Now if we think about this situation, our energy before and energy after, I do not have any gravitational potential energy because this is not moving vertically. Now when I'm at this x equals 0 point, the only thing that I'm going to have is kinetic energy. If I think about this moving back and forth forever and ever, when it's in this middle part right here, it has my maximum velocity, but it does not have any elastic potential energy or spring potential energy. However, when it's extended to its maximum point, that is when I have my spring potential energy. I can write down this equation as 1/2 mv squared equal my spring potential energy, which is 1/2 kx squared. And from there, solve for whichever variable that I need to. We went through all the different situations we can have for conservation of energy. Now we'll start applying it to some real life situations and you'll work on some hands-on pieces.